Okay, how are you? We are still on discussion of galvanic cells, and now we will be exploring the cell potential. I have here a given reaction, okay, and we will be exploring this alongside with learning back some of the concepts that we have seen from the previous videos. Now, the first thing that we know about galvanic cells is that they are devices that are used to generate electricity, making use of a spontaneous redox reaction. Okay, we've learned that before. Now we will see if this particular reaction here can be constructed as a galvanic cell, also known as voltaic cell. You already know that. So that means that we have to have the reaction between the ferric ions and a copper solid to produce copper ions, cupric in this case, and the ferrous ions. So that means we have to look into the standard reduction potential table and see what we can say about their, reduction tendencies. So on the table, we will see that the reduction of the ferric ions to ferrous ions would have a potential reduction of 0.77 volts, okay, as opposed to the reduction of copper ions. Remember that what we see on tables are all reduction potentials, so that we can look into their relative strengths. So you have their copper solid with a reduction potential of positive also 0.34 volts, okay. So when we see these two half reduction reactions and compare their reduction potentials, meaning their tendency to pull the electrons, that means that the ferric ions win over the copper ions in terms of, pulling these electrons. Therefore, we have to retain this, okay? And this will be the reduction half that will happen and not this one. So as we know in redox reactions, if there is a reduction, the other one has to be oxidation. In other words, this has to be reversed so as to be able to construct a cell from these two reactions, because this already wins over this, okay? So when we do that, we reverse this reaction and say copper solid now can be oxidized to copper 2+, liberating 2 electrons. And therefore, we will be writing down the potential of this half reaction. Now that this is an oxidation, we'll just put there oxidation potential becomes negative 0.34 volts. You see here, we reverse the reaction, and therefore we also reverse the sign of the potential. We are not doing reduction for copper now, we're doing oxidation, okay? So look at this one. This is the reduced form of copper in this particular situation. This is the oxidized form of copper. So that's from 0 oxidation state to +2. Now, we will be labeling this as our oxidation half reaction. OHR stands for oxidation half reaction. And therefore, the other one who wins in the battle earlier, if you remember, we will be labeling that as our reduction half reaction. So nothing has changed there. I'm just copying this. So that's Fe3 plus an electron forming Fe2 plus. Okay. And this one is the reduction part here. Look at that, oxidation, reduction, and it's still positive. We are just copying that. It's happening on its own. Now, if we add these two reactions, okay, we will see that copper is actually giving up 2 electrons because ferric ion is stronger in terms of reduction, right? But this one only requires 1 electron, and therefore we need to balance the number of electrons involved. Remember, this is a tandem, okay? The number of electrons lost is equal to the number of electrons gained, as we learned it from redox reactions before. So what we do is to balance the reaction, which means that I need to multiply everything by 2 right? 2 here, 2 here, 2 here, but I'm not touching this. Okay, there's a reason for that later. Okay, remember, when we reverse this reaction, we change the sign. Very similar with what we do with enthalpy and Gibbs energy. Remember Hess's law? Very similar technique. We balance the reaction, okay, but we multiply this and we did not change the value. We can only change the sign, reverse it, but not multiply by a factor. Why is that? Because these values in the standard reduction potentials are generated from a reference electrode known as the hydrogen electrode, and we will be discussing that soon. Okay, so when we are computing for the E cell, which is practically adding this reaction, we are not multiplying these standard values by any factor. We can only reverse its sign when we use the equation in the reverse manner. Okay, so let me just copy this. So that's, we have copper solid plus 2 ferric ions forming copper 2 plus, and therefore 2 Fe2 plus aqueous. And therefore our E cell, which is the sum of the potential of the reduction and oxidation, leads us to what? 77 minus 34. So that's 7 minus 4 is 3. Okay, 7 minus 3 is 4. Now that's 0.43 volts, which is still positive 43 volts. Now, a positive value for the electromotive force of the cell. If it's positive, that means this reaction is occurring spontaneously. Okay, so that will be our basis for spontaneity when we talk about electrochemical cells or galvanic cells. In chapter 17, we said that if the delta G naught is negative, that means the reaction is thermodynamically favorable. So here, this is thermodynamically favorable when we see the E cell to be positive. So this reaction is written here, right, is consistent with what we have derived. So definitely, we can construct a voltaic cell from this reaction because an E naught is positive. Okay. Now let me just push this a little bit to cell notation. Now here, we already have written our oxidation half and reduction half. Remember that we can write a cell notation to separate the oxidation half, salt bridge, reduction half. Okay, so let me try doing that. The oxidation half here is copper and copper 2 plus. So I can write, say, copper solid, right? And solid to aqueous. Therefore, I'm using a vertical bar to differentiate the physical phases, right? Copper 2 plus, aqueous. Now, this is the anode half cell, where oxidation happens. Okay, this is our physical boundary that separates the two half cells. And then the reduction is from where? From Fe3 plus to Fe2 plus. Fe3 plus, aqueous. Now, since this one is also aqueous, I cannot use a bar. What we are using conventionally is just a comma, because they have to coexist in the same mixture because they are both dissolved in liquids, right? So Fe2 plus. Now you would say, where's the electrode there? Now the fact that our chemical species reacting on the cathode half are both dissolved in solution, therefore we need an electron sink that can transmit the electrons or receive the electrons coming from the anode half. So we need a platinum metal. Platinum is non-reacting in this case. So look at that and put a bar there. So if you were asked, which one is the anode? Your copper is your anode, right? So it's the source of your electron. The electron will travel through an external circuit. It will be connecting to your cathode. Your cathode here is the platinum, right? So the electrons will travel and will be caught on by your substances here. Ferric ion getting reduced to ferrous ion. Okay, so what we have learned here, number one, is that we should be able to decide which one will go reduction and which one will go oxidation based on their reduction potential table. So when we flip a reaction, we flip the sign as well. When we multiply the reaction by a factor to balance the number of electrons or the chemical species, we are not multiplying the reduction potential. We are only flipping the sign. And why is that again? Again, we said that these values are derived from reference electrode, which is the standard hydrogen electrode, which was put into 0. So we will be having our own discussion on that as well. Okay, so if the cell potential gives you positive, that means this is a good to go for a galvanic cell. And then we have learned a new thing here when we write the cell notation, right? The bar separates physical boundaries. The double bar, you see, okay, there's a salt bridge here, is actually telling us the two half cells. And if the reacting species are both in the same phase, we cannot use a physical bar like this one. These are all liquids. But if it's between two solids are totally different from each other, and therefore we can use a bar. So this is quite specific for liquids because they are completely miscible. Okay, so you see here the cell notation or the cell diagram tells the story, so you can visualize in your head what happens in this particular galvanic cell. So electron transfer from the anode half, where, let's finish this up, where oxidation happens, and of course here, this is where reduction happens. I hope this helps. Sorry, I'm always wearing my fat suit, as you know it.